So most generally we have been representing the signal into the time domain as f of t, and the same kind of the same signal represented into the frequency domain by f of either omega. So omega is the angular frequency here. So let us imagine that there it is a certain signal f of t, which is basically a complex valued function, and that represents some kind of the signal. So here initially we are having the signal information into the time domain here. Now, as we have covered in the previous topic where we have seen the continuous Fourier transform, so thereupon we have the two mathematical formulation, the forward Fourier transform and the reverse Fourier transform. So forward Fourier transform will get the input as f of t and provide us the output as f cap of omega. So we have been switched from time domain representation to the frequency domain representation. So here we have f cap of omega is equal to, that we obtain from 1 upon 2 pi multiplied to the integration minus infinity to infinity for the product of f of t with the complex exponential e to the power minus I into t into omega dt here. So this way the Fourier forward transformation is utilized here for, let us say, decomposition of the signal information into the respective frequency components here. So on other hand we have the reversal of this. So we say that this is inverse Fourier transformation, the reverse way to the forward one here. So mathematical expression here it is provided where we write f of t we can get back from the Fourier domain or the frequency domain by computing 1 upon 2 pi multiplied to the integration minus infinity to infinity for f cap of omega into e to the power I t omega d omega here. So this is a set of two equations generally we identify as the continuous Fourier transform. So now the question is, how do we exactly analyze the information of various kinds in real-time scenario by this particular mathematical tool here? So this inverse representation or the inverse Fourier transformation, we can have interpretation as writing simply f as a superposition of the time harmonic waves we have been denoting by e to the power I t omega. So in this particular representation, for any example of the signal, if we obtain the corresponding Fourier transformation f cap to be large enough, and that will be near to some of the frequency component value in the graphical representation also we can show. So that time we come to see that or analyze that the signal is having a large component that is periodic with that particular frequency value here. So now when we are dealing with only periodic type of the signals, so this particular approach will be okay. But when we are having few of the aperiodic type of the signals in various applications, for example the speech analysis, so that time there it is also a necessity that we will like to have localization of the frequency components into the time parameter as well as into the frequency domain. So in this concern, the Fourier transform will not be a better option to use for such signal processing applications here. So now what is the alternative with us instead of going for the continuous type of the Fourier transformation? So we have currently the two options. The first one is another form of the Fourier transform that is identified as the short time Fourier transform, also known by windowed Fourier transform. So for windowed Fourier transform, the abbreviation we prefer, that is WFT in capitals, whereas the another name short time Fourier transform, there it is capital STFT here. Now this is one alternative. Another alternative which is more evolved than this is the continuous wavelet transform. The first exact topic for understanding the wavelet theory, and onwards we shall have a focus on the Haar wavelet, the simplest one. So this is CWT, continuous wavelet transform. So what is the benefit of either using WFT or STFT or the CWT for such applications here? That in these two tools there it is a mapping of the function or the signal representation of one variable type, most possibly the time we take, into the function of two variables, the two variables with regard to the time and frequency here. So how do we make the analysis? So in general, for example, if we have a large value of the transformed representation near a time parameter and the frequency parameter, so this is interpreted as the signal under consideration is containing a large component with the frequency certainly omega near the time t, and this is way we are having the disadvantage of the Fourier tool, the conventional continuous Fourier tool, overcome by the use of either windowed Fourier transform, also known as short time Fourier transform, or next to that the continuous wavelet transformation, and there are many more versions into the wavelet family. So this is what this particular topic it was, continuous time frequency representation of signals here.